So that's somewhat a very general path that the solar eclipse will be taking. And we'll go ahead and get started with the webinar today. We are looking at the first coast-to-coast solar eclipse in over 40 years. And our outline of today's schedule agenda is we're going to look at the study of the sun. We're going to talk about a little bit the SDO, which is a current NASA mission that's observing the sun. We'll look at some solar eclipse basics, safeties. We'll talk about some different activities you can do, as well as the NASA eclipse activity guide. And then there's information at the end regarding looking at the solar eclipse through the eyes of NASA, as well as outreach activities for NASA. You will also be able to download today's presentation at the end. It is, I'll give you a link for that so that you can get all of that information. This PowerPoint has all sorts of different information in it. Here's NGSS practices. Before that was the agenda. To me, that just makes it more helpful as a teacher to have that information when making a lesson plan. Also, within the notes section of the PowerPoint, there's additional information, whether it's web links or maybe some of the comments that I'm saying. So when you get the PowerPoint and download it, be sure to check out the notes section of the slides. And if you're not sure what that is, shoot me an email and I can tell you about it. But there's additional information there. So in looking at the solar eclipse, when we go back and we talk about eclipses and the understanding of early scientists' works, the Greeks were perhaps the first to study our satellite scientifically. And when I say our satellite, I'm referring to the moon. And using Earth's shadow on the moon during lunar eclipse as a guide, in the 3rd century BC, there was an astronomer who was able to estimate that the Earth, that the moon was 60 radii away from, and what we found out is that while that was a great guess, it does in fact vary between 55 and 63 Earth radii away. So the moon does receive its light from the sun, and the Earth is positioned at a point in the center of the sphere in which the moon moves. And because of that, we only see half of the moon. So just a couple of really cool, in my opinion, moon photos, time lapse. This one here by NASA photographer Bill Engel, the super moon. This was back in 2011. It's called super because it's so close and so big. It was the closest and biggest it's been since March of '93. And then in talking about the different projects, that kind of gives us some info about the moon, but about the sun and solar eclipses, this is actually from SDO and NASA Heliophysics. So that's just some neat aspects of coronal mass ejections and different things that we have seen from the sun. Um, and in looking at SDO with what is going on there at the sun, there's all sorts of different sun facts that we can take a look at. Um, we can talk about that it's approximately 4.6 billion years old, halfway through its cycle as a star. And we could talk about life cycles of a star, which is actually a topic that is covered in at certain standards within the classrooms. But I'm going to give you a few other slides here that give you some more information about why I study the sun and so forth. And these here are available for you for information if you need it. The main thing that you need to remember is that the sun is extremely, extremely intense light, and you should never look directly into the sun without approved and proper glasses. We'll talk about those a little bit later on. But with modern physics, we're able to see the sun in different temperatures, in different, as we see, like, if you see the rainbow, if you kind of split that into the spectrum, you can actually take pictures of the sun in different colors. And that's one of the things that SDO, or the Solar Dynamic Observatory, does. It was launched in 2010. It's one of the largest solar observing spacecraft ever put into orbit. It has 6 cameras that take photos of the sun every 3/4 of a second. So if you want to do some math with your students, there's your great math problem. I love the fact that the camera is ideally seen on a 5-foot by 5-foot. I want the TV that size in my house. That's life size. Well, it's not life size for the sun. It would be like the size of a human, 5-foot by 5-foot. But anyway, in the first 5 years of existence for SDO, just one instrument has taken over 100 million images of the sun. So while we don't know everything we need to know about the sun, SDO has tremendously helped in that. And one of the things that this solar eclipse is going to give us is a wonderful opportunity to do more research on the sun. And towards the end, I'll refer you to some different ways that citizen scientists are getting involved with the eclipse, and ways that you can have your students be involved as well. Yes, it is taking photos through different color lenses, and there are, I think, 9 different ones, and I'm just going to click through them here, and you'll see with each different color lens you see something different. The prominences on the outside of the sun kind of changes based upon which temperature it's in. And so and I'll go back through those right quick. So that allows us to study the sun in different ways, because as you can see, each photo is different. Even if you just watch those sunspots that are there, the sunspots from 10,000 K to 50,000 K, they go from black dots to, well, they're not really there as black dots. And then here at 0.6 MK, you can see more of the loops and swirls. So just amazing what technology has allowed them to do. I've got a short little video here that's actually showing a CME, or a coronal mass ejection. Actually, that is not what I have here. That's part of what we had seen. When you get the actual PowerPoint, this slide here is actually embedded as a CME, so that it's actually, you can actually see that loop out like it did in that previous video. And that was SDO. They call it doors open, first light. It was one of the first CMEs that they got a picture of with that. But in talking about those coronal mass ejections and talking about what's radiating from the sun, there's several different types of radiation that's coming from the sun. You've got UV and ultraviolet, which can get from the sun to the earth in 8 minutes. MK stands for million Kelvin, so 0.6 million Kelvin, that would be like 600,000 Kelvin. Sorry about that. The charged particles get here in 10 to 30 minutes from the sun, and then magnetized blobs of solar material can take 18 to 96 hours. Now, I do want to give credit. the information that I'm sharing on the slides that have the panel like this over to the side, kind of an open view to the universe. Those we're taking with permission from a heliophysics presentation of Dr. Lika. And so this magnetized blobs, while that doesn't sound like a very scientific word to use, that is the official terminology that you use. And granted, it takes 18 to 96 hours, but from that we get our auroras, geomagnetic storms, but we also have to watch out for radio disturbances with that. When you talk about charged particles coming from the sun, here on Earth we're protected by the Van Allen belts, but outside of the Earth's atmosphere and outside of the Van Allen belts, up where the International Space Station is floating, they're not protected by the Van Allen belts. And so whenever there's radiation and charged particles coming through space, they have to monitor that space weather to make sure that they're protected. And there's areas within the space station that they can escape to, and maybe escape isn't the appropriate word, but that they can go to better protect themselves. A lot of the all the hardware that's sent up to space is radiant hardened. In other words, it goes through a special process so that it's not as susceptible to radiation. Because again, whenever you go outside the Van Allen belts, whenever you leave Earth, you're losing that protection. And radiation can cause satellite drag and radio blackouts, but radiation can also be detrimental to our health, to aviation, satellite functions, and again, it's what helps produce those amazing auroras that are available to be seen. Telescopes in space. From space, we can see UV light and UV and X-rays. And again, SDO has been there capturing that for several years now. And in these photos, you can see various loops and swirls, and those are moving along magnetic field lines. So it's allowing us to learn a whole lot more about the sun. And there's some upcoming there's a new project that is set to be launched to study the sun as well. I've got more information about that in the towards the end. This is a photo from a total eclipse back in 2002. You can see the prominences off the limb in red, and when the moon blocks out the light, you can see much more subtle evidence of a corona. And if you are in the path of totality, you will be able to see this. If you are not, you will not. Even if you're at 99.9% totality, you will not see this. You have to be in the path of totality in order to be able to see those few prominences off the limb there in red, and then the subtle evidence of the corona with the shadings going around the edge. This is an example of a lunar eclipse, just to kind of help your students understand the difference between solar and lunar. Many solar system bodies partake in eclipses, transits, and occultations. Here's Jupiter's moon casting a shadow on its cloud tops. This is from 1973. This is a transit of the planet Mercury across the face of the sun. This is from 1882, and that's Venus going across the sun. The Earth is very unique in that where we sit and the current perspectives of where the sun is, the size of the moon, and the distance away from the sun that it is, that we can actually have a total eclipse. We are the only planet within our solar system that, because of the way our moon is situated both with orbit and in size, it's a perspective thing, that we're capable of having a total eclipse. I'm told that the moon is slightly moving away from the Earth about a half inch a year, and that eventually it'll be too far away, the perspectives and the numbers will be off as far as that it won't be able to produce a solar eclipse, total solar eclipse. It will be able to do an eclipse, because an eclipse, that just means the Earth has to come between the Earth and the sun. But as far as a total eclipse, you know, million years from now, that's not going to be happening. But I think we're okay from now. This is a photo here at NASA Armstrong where I'm at. We focus on flight, and this is a photo of one of our airplanes producing a sonic boom. So you're seeing the shock wave there, and what's the background there is that of the sun. So this is a photo of one of our planes eclipsing the sun, and that's the Schleringer photo technique. So just a couple ways to tie it back to some of the information that we do out here. So where are you going to be on August 21st, 2017? While the total solar eclipse does go from Oregon on the west coast all the way down to the east coast, and it does cross the entire U.S., not everyone is going to be in the area of a total eclipse. But all of the continental United States will be preparing for a partial eclipse. And that's, I think, a very unique setting. Have you seen an eclipse before? Do you know what's going on? And again, there's information within the notes section to kind of talk about those. But I'm going to assume as teachers that we're good there. If you need more information and the notes section doesn't help out, you can gladly just shoot me an email and I will do what I can to help you there. But truly the basics of the solar eclipse and the lunar eclipse, you've got 3 items involved. No, they are not to scale. The sun, which is the center of our universe and doesn't move, but the moon and the earth somewhat change positions. And for a solar eclipse, the moon is in the middle. For a lunar eclipse, the earth is in the middle. And so it's a very simplified drawing, but to just kind of help think about things, I often think about doing some cross-curriculum integration with the PE teacher and playing monkey in the middle and yelling out solar eclipse, lunar eclipse, and having the students get into the proper settings with that. This is a map showing the total solar eclipse paths from 2001 to 2025. You'll notice the one that's going all the way across the U.S. is August 21st of 2017. Now in 2024, it's coming up and it'll go from Texas up through Maine, but that's not going to hit the U.S. as much as the one this particular, what are we, 9 days away from the solar eclipse. So just kind of give you an idea of the path of totalities for different solar eclipse. So I've got a couple of different setups for the total eclipse in terms of showing the mechanics. I've left both of them within the PowerPoint. That way you can use whichever one you feel is best. But if you'll notice in the dark area directly behind the sun, that's called the umbra. And that umbra, whenever I first showed you the video, it showed you a very tight circle. And then here on the edges, the penumbra, that's where you get the partial eclipse. And that is estimated to be 70 miles wide. And that, again, all of the continental United States will fall in some aspects of that partial eclipse during that day. So this is the first total eclipse visible in the U.S. in 38 years. And it's the first time the eclipse has gone coast to coast in almost, I think, 99 years. So this next video shares a lot about the details and just how grateful I am that the technology that we have.
What we're talking about is several visualizations of the path of the moon's shadow during the eclipse in 2017. Everything in it is driven by the data. So the color of the ground, the position of the path of totality, the lighting from the sun angle, all of those are things that are based on data. A lot of NASA products were used to create this visualization. I used the Lunar Reconnaissance Orbiter, the laser altimetry data from that, which gives us a digital map of the elevations on the moon. For the Earth, I used something called SRTM. This was a radar that was flown on the space shuttle. For the positions of the Earth, the moon, and the sun, I used a JPL ephemeris. An ephemeris is just a list of positions, but it's the most accurate tabulation of those positions. This visualization is unique because it shows the effect of both the irregular edge of the moon, the limb of the moon we call it, and the elevation of the observer. Now, we've known for a long time that the elevation of the observer affects where the shadow is. We've also known that the mountains and the valleys along the edge of the moon affect the shadow. So you may have seen on eclipse maps in the past that the image of the umbra, that shape of the shadow on the Earth, is drawn as a smooth oval. But we know that the moon isn't smooth. Around the edge of the moon, we have these sort of jagged peaks and valleys. And a peak can block the sun a little bit earlier than you thought, and a valley can let the sun in a few seconds longer than you thought. The combined effect of these peaks and valleys is to create a shape that's not really an oval, it's more like a polygon. But it hasn't actually been seen in exactly this way before, where we calculate those circumstances for every point on the map and draw that shape. Totality is that 2 minutes or 2.5 minutes when the moon completely covers the sun. The sudden darkness of totality is just something that a lot of people can't compare to anything else. I love the idea that I'm giving this kind of map to other people, and especially that it's more detailed and more accurate so that people are actually in the right place to see it.
Again, I think that is just absolutely amazing what technology we're able to do. And while that may not be a video that you share with a kindergarten class or an early elementary class, I'm just thinking the conversation and talk that could bring about in a physics class or a geometry class. I just think there's so much that's there, and how they're triangulating and bringing in so many different levels of science. Anyway, I just kind of totally geek out whenever I see that one. So what does it look like from space? And this is a couple examples of what a solar eclipse from space would look like. You can see the dark spots on the Earth. And I'm actually going to show you an activity later on today, or later on in the webinar here, that by using if you have a Earth, whether that's a globe or a even just an inflatable Earth ball, that you can simulate the sun and the moon and actually cast a shadow like that, which is really kind of cool for kids to actually be able to replicate an actual photo like this that you could see. Different phases of a solar eclipse. This is a series of stills from 2013, and it shows the eclipse sequence from right to left. The center one right here is only available in totality. If you're not in totality, you will not see that one there. So if you can see as you move left to right, you know, this is the last little bead and this is the first little bead coming out. But even though there's that one little ray, you don't get the prominence around the sun that you do when you're in totality. So what may you see during a total solar eclipse? Again, if you're in totality, you've got these prominences. You've got polar flumes. You've got the corona. You've got the helmet streamers. You've got coronal loops. And, you know, if you're not in the path of totality, this is kind of what you get. You just kind of get a little bit of a bead there. So to me, it's totally worth making it to the path of totality. And that's part of my process for I'm going to Tennessee. I'm going to be in Cookeville. My goal is to be there to see the total eclipse. But again, everyone's going to be able to see a partial eclipse, provided that the clouds are out of the way. Again, this is another example demonstration as far as the mechanics of a solar eclipse. Again, it's not to scale, but you can see again the umbra and penumbra, so you can see where it's going to be totally dark, and then you can see where we're going to have a little bit of the partial eclipse. Here in California, which is where I'm located at, We are looking at about 80%, 70% partial eclipse here. And you can see up here is where the total eclipse is. If you are in the center on that red line there, you'll have up to 2 minutes and 40 seconds of totality. If you're on the edges, it could be as little as a few seconds. So the closer you can get to the center of totality, the better. I saw someone earlier was asking about locations for glasses and so forth. You don't have to have just glasses in order to see the solar eclipse. You can actually project the images using pinholes or with a filter. Also, there's going to be live streaming of the event. So if you're not in the path of totality but still want to see what it looks like in the path of totality, again, I'm going to say I'm so thankful for this day and time in which we live of technology. And towards the end, there are activities that teach you how to make these pinhole projectors. They also have 3D printed ones. NASA has uploaded the STL files to the website so that you can actually download the STL file for your state or for the country, and that's created and ready to go for you there. But you can also observe directly with filters. And that would be the Eclipse glasses. These are not sunglasses. And while they say Eclipse glasses, I'd like to say that these are really what we call solar viewing glasses. And that means that it's safe to look at the sun with those. If you have a class set of solar viewing glasses, please don't throw them away after the eclipse, because you can take those, and when you're studying the sun, you can still take those solar viewing glasses and go out with your students and take a look at the sun through those glasses. Now, I will tell you, don't try to walk with those glasses on, because unless you're looking directly at the sun, you're not going to get any light coming through. But you can still use that. The cool part about the eclipse is that the sun's not going to be a perfect circle. And that's what makes it so intriguing to take a look at, because it is an abnormal shape. And so because of that, it's all the hype of, ooh, these are eclipse glasses. But what I would say as an educator is that you can still use those eclipse glasses, those solar viewing glasses, to take a look at the sun at any time. Again, just make sure you don't look at the sun without having appropriate glasses or filters on. And if you have access to welder's glasses, the number 14 is safe for viewing. There's additional care that can be taken for optics. I'm not going to go into that, but that is available if you need it. Here at NASA, we're all about safety first. Eye safety first, eye safety for your devices. And I'm going to show you a couple slides about when to wear your glasses and even talk about event safety. So it's important that during the eclipse, again, that you never look directly at the sun. I know I've already told you that a couple times, but again, I want to drive home, unless the sun is completely blocked out, which is for that maximum 2 minutes and 40 seconds totality, you need to have the glasses on. If you need more information about it, there's a website there, eclipse2017.nasa.gov/safety. And again, it can last up to 2 minutes and 40 seconds. In looking for glasses, there's two things to look for in buying your glasses. Make sure that they are ISO compliant. That's the particular number there, but that's from the International Standards Organization, or that they are CE certified. Either one of those two items lets you know that those glasses are appropriate and safe for you to use. When to wear the glasses, again, just kind of showing you if we narrow this down to 5 different aspects. You've got the partial eclipse on the first part, whether that's 1% or 90%, that's considered partial eclipse. The Bailey's beads, that's what that last little stream of light coming through, just that last little bead. The diamond ring is where there's literally just like one ray still coming. And then the fourth is totality, and then final stages whenever you come back. This here is all 4 of those stages you need to wear your glasses on. But the totality, that's their number 4, is the only time you can take the glasses off. So again, if the totality is not where you're at, you need to remind your students or whoever you're with that the glasses stay on at all times. Safety plans, if you're creating an event, there's actually a website that you can go to get information about event planning, crowd management, transportation, emergency first aid, and also a PDF that gives you some more information in regards to safety. So, what are some activities that you can do with your students in order to be able to do activities leading up to or even after the event? And this particular website, spaceplace.nasa.gov, has all sorts of different activities, and you can see these are actually little icons: Earth, Sun, Solar System, Universe, Science and Tech, and for educators. And if you click on the Sun one, there's all sorts of different activities. I've just kind of did a screenshot here, but making the sun paper, I think that's making the sun paper is a really cute little activity that can be done, and it also takes into account some of the artsy side of things. So instead of being a STEM event, it could be more of a STEAM event. So to make sun paper, you need red and yellow food coloring. You need shaving cream. I know I just said shaving cream and we're talking about an activity for kids, but it is really kind of neat. Even as an adult, it's really kind of neat to do. So just some sort of protective paper. We used wax paper down on the table, and you put out enough shaving cream to fit inside the ball of the hand. You don't want it really tall. You just want enough there that's kind of in a circle. And then after that, you use a little toothpick to kind of spread it out a little bit. And after you've spread it out, kind of, lowered it down so that it's not a mountain of shaving cream, kind of spread it out a little bit. You add 5 drops of red and five drops of yellow. Use the same toothpick to swirl around and allow the students to swirl as little or as much as they want. Once they've done that, you take a piece of cardstock paper or art paper, place it over top of it, remove the paper, and you'll notice over here on the left what you've got is you've got the majority of the coloring you had, but you've also got some shaving cream. And so what you do is you take some of that shaving cream and use a ruler to just kind of push it off. And as you push it off, it produces an amazing, cool little photo. And I know I'm talking shaving cream with students, so yes, you have to be cognizant of the level of your students and whether or not you really want to give them shaving cream. But I will tell you, this is really a neat and amazing activity, and a lot of the packets that I've seen for the coloring, as far as the yellow and the red, unless you get the large bottles of yellow and red, you can get a 4-pack that's yellow, red, blue, and green. And what you can do with the blue and green is you can then make Earth paper on Earth Day using, again, the yellow and the green. So the next set of activities I want to show you are from the NISE network. NISE is the National Informal STEM Education Network. And so they have 3 different activities. And on the NISE network, they have where you can download these. They have videos to go with them. They have information. One of the things I love about them is I think that the manipulatives that you need in order to do the activities are easily to come about with. The first one's called Bear's Shadow. And basically what you're doing is you've got a little green mat. And if you don't have the green mat, you could have the students draw their own. And on that green mat, there's a little pond with fish in it. And there is a early childhood book called Moon Bear's Shadow, and this activity actually refers to Moon Bear's Shadow. And then there is a tree. I actually had a friend of mine duplicate this, and she used Christmas ornaments and she had little Santas and elves that she used instead of the bear, and the trees that she had were from her Christmas collection where she decorated at Christmas, so she didn't have to go out and buy anything particular for it. And while that looks like a flashlight with a big sun on the end of it, it literally is just a flashlight. And so with that, you can actually test where the shadow is at. And it allows the students to see how a shadow is created when an object blocks the light from falling on the surface. So if the sun is behind the tree, you get a shadow of the tree. And it asks them to, there's different challenge cards of, you know, how can you get the bear shadow to scare the fish or to not scare the fish? Where does the sun have to be in order for there to be no shadow? Where does the sun have to be for there to be a long shadow? And I will admit, because I taught 20 years at the high school level, when I first saw this activity, I'm thinking, I could never have my high school students do this. This is so simplistic. They would laugh at me if we did this activity. Then I did the activity, and I'm thinking, that is such a mentally challenge to take what you experience kinetically and with your hands and what you're seeing, and then to mentally have to relate that back of, okay, that long shadow, ooh, that's sunrise. And, the short shadow where there's almost none, ooh, that's at high noon. And to really think about what we know and experience on a daily basis, and then to actually recreate that is really, I think it's really worth doing. Um, and if you want more information about that, I've actually put a link over here to the far left, the Vimeo link. They actually, the NISE network created 2 different videos, one that you can use to either just introduce the video to whomever you're doing it for, and then there's another one that allows you to learn about um, the actual activity so that you can teach it as well. And they do that on all 3 of their activities. All 3 of the slides have that link. The next one's called the solar eclipse. If you'll remember, I showed the picture of what a solar eclipse looks like from space. And so on a sunny day, you can actually make this model outside. You can actually grab the sun, not grab the sun, you can grab an earth, and then basically that's a moon ball or a ball on a stick. If you don't have a moon on a stick, we grabbed a piece of yarn and put a pencil up in it. You can also do a styrofoam ball. I will say don't use a ping pong ball, because if you use a ping pong ball and a flashlight as opposed to the sun for this event, it doesn't totally block out all the light. It's a little transparent. So this here, and if you don't want to do this outside, you can do this inside. And so what's really kind of cool about this is you can actually have the students create a solar eclipse. And again, if it's bright enough outside, you can let the sun be your source. If not, you can use flashlights. And where are you going to come up with all those flashlights to use in your class? Well, if your students have their handy dandy little phones with them, most of the phones these days come with a bright light on them, which is quite amazing. The third activity from the NISE network that I wanted to highlight is called Big Sun, Small Moon. And it's using a tennis ball and a inflatable beach ball. And honestly, you could use a beach ball and a tennis ball for the previous activity as well. I think it's just cooler if you actually have the earth ball. But where do you need to move in terms of to get those to be the same size? Because the reason we're able to experience that total eclipse is that the perspectives and the dynamics in terms of how far the moon is away from the sun and the size of the sun actually fits and makes it work. And so have the students go back and forth, hold up the tennis ball. How far apart do you need to be in order for the tennis ball to totally cover up the beach ball? So Dawn, that's a great idea. And so these are some really great things. The extension that I love on this big sun, small moon, because you're talking really perspectives, is what other, types of photos can you take of perspectives out there? And especially higher level students, especially math level student, some of the math students, when talking perspective of things, to have them literally go out and take photographs of different perspectives so that they can see the depths of things. I don't know if you've ever seen the pictures where there's a Leaning Tower of Pisa and somebody's holding their hands up like they're catching it. Um, or just putting their hand on the side of a building and it looks like you're holding it, or even catching a sunrise and acting like they've caught it in their hands. So those are some of the photos that could help with understanding these aspects of perspective and relative size. So another upcoming event for NASA is the James Webb Space Telescope. And with that James Webb Space Telescope, they have produced a life cycle of a star bookmark. And I will give you the link to that, is in the notes. And you can actually use pony beads and yarn or tape or a cord. I prefer using a chenille strip, or a pipe cleaner as they're often called, for the students to make a life cycle of the star bracelet. And so you talk about the 8 different steps to the life cycle. Now this is a slide that has that, and you can see it over here to the right. But if you'll notice, let's look at blue. That's kind of short. Gravitational energy powers the young star. If you look at this in the middle, what's in the middle here, that's actually the life cycle of a star bookmark that I was talking about. And if you'll look at the verbiage for blue, it says gravitational energy. So the same verbiage that's on this bookmark is also the same verbiage that's on this slide right here. So if you don't have the resources to print out the bookmark, you can just use this PowerPoint slide. So whenever I first started this, I will confess that I thought, ooh, I'm going to need twice as many green beads as I am the rest. But whenever I started creating it, if you put a green on at the beginning and a green on at the end, when you tie it together, you end up with 2 green together. The whole point that it is a cycle is that whenever you get down here to number 8, the green, that's also the green as number 1 right here. So in making your bracelet, you don't need twice as many greens, and I share that because that's something that I dealt with. Ginger, you will have access to the PowerPoints and videos later. All of the videos are embedded within the PowerPoint, so if you get the PowerPoint, you've got everything. At the end of the program, I will give you a link to where you can download all of this. I'm going to give you a link actually to a Google Drive because there is so much. So again, and then the other pictures next to the bookmark, which in the middle is just various other pictures of the star. The other thing that NASA has produced is a 2017 Eclipse activity guide. And with that Eclipse activity guide, there are actually 14 different activities. And for the sake of time, I am going to summarize those. Living in a bubble is talking about magnets and a compass. Sunburn is talking about UV detectors. Seeing the invisible is talking about infrared light detectors, such as you can do that using smartphones or TV remotes. Seeing light in a new way is a diffraction spectra. The 5, a light snack, that's making a cookie box spectroscope. The Girl Scouts of America actually partnered with NASA in helping create this Eclipse activity guide, so that a light snack, which is a cookie box spectroscope, the Girl Scouts created the spectroscope, so of course they used a cookie box. You could also use a cereal box as well. But making sun s'mores, that's using a solar oven. But I will tell you, there's also activities out there where you can use a Pringles can, and whether you want to make s'mores or make a hot dog using that Pringles can, that's possible. The really thing that's neat about the Pringles can is that the inside of that is already lined with the aluminum foil, so you get the reflection there. Number 7, how big is big? That there's talking about a model of the Earth to the sun. Earth as a peppercorn is another size and scale of the solar system. Then number 9 there, the sun tracking, that's making a pocket sun clock. And for younger kids, You might want to chalk the shadow at 8 o'clock in the morning and then chalk it again at 11 o'clock and note the difference. In the link that I'm going to give you for additional resources, there is a PowerPoint that has activities for lower aged, younger aged classes, or some of the lower level classes, and with those they talk about some of the different activities that can be done with that. It's called Emblem Eagles Eclipse Unit, and Maria Blue has allowed me to share that information with you, so that's as part of that document as well. Waxing and waning is talking about the phases of the moon and eclipses. How do eclipses work? That's showing you how you can use a yardstick to actually simulate the eclipse. When day turns to night, that's measuring light levels and temperature. Making an eclipse viewer is literally what it's teaching you how to do. The 14 eclipse chalk art, again, is allowing bringing in the A from the aspects of STEM to STEAM, and this is the activity book right here, and again, you're going to be able to download that at the end. You've got all the different resources, how to use the guide, some of the aspects about it. So here's the living in the bubble, and I'm just going to quickly scroll through this. I'm going to show you a little bit more about the UV beads, but you've got a lot of the background. So as an educator, this is very easy, in my opinion, to be able to come up with if you need to do a lesson plan to go along with it. Again, the cereal box, spectroscope, they show it here as a cookie box. Either way works. Making s'mores, again, that could be done with a Pringles can as well. The solar pizza is just basically looking at the size. And so then I want to go ahead and get down to the bottom. Whenever you get down to the bottom, give me a second here. This shows you another picture that I'd shown you earlier as far as what you can see with the total eclipse. You've got an eclipse guide. You've also got some safety information there, and then other safety info to kind of help you out, and then additional links that can help you for the solar eclipse, different website resources, even more resources, a complete list of materials in terms of what's reusable, what you'll need. So really just I think that NASA has done a great job with creating the activities that are there. So the solar bead activity, the UV bead activity, we can see the effects of UV rays on our skin through like a sunburn, and we can protect ourselves by wearing sunscreen or taking other actions like putting clothes on. But using UV detecting beads can be useful for the students to help them understand what we're getting from space, whether that's shielding for the astronauts that are on the ISS or just understanding how we need to protect ourselves from the sun. And so this is a UV activity. You grab detecting beads. I've just bought them off of Amazon. If you get the ones that are UV detecting beads and also glow in the dark, they tend to, from my experience, be a higher quality bead and react better. You can do this either using the sun for your source of light, or you can actually buy UV lights. Just know if you buy UV lights that, just like looking into the sun is damaging to your eyes, UV light is damaging to your eyes as well. Sunglasses, sunscreen, water, Ziploc baggies to make things clean. I have students do preflections, and I give them the little setup of what we're going to do, and then I have them, what do you think is going to happen? And I literally make them write down their answers. The preflection really makes them think about, what is it that we're going to do? And I think the preflection makes the learning process extremely rich, because once they've gone through the preflection, what they think is going to happen, then they actually do the activity. So they'd have various stations where they go and expose it either to the sun or expose it to the UV light, and then they get to record what actually happened, and then you come back at the end and write reflections. How did it happen? How did it make a difference? And while I give you a list of different stations that you could have, if you have a lotion that has the SPF in it, if you have especially your older teenage girls that use makeup, because some makeup comes with SPF in it. So literally have them put that on the beads and see with the UV light or with the sun, does it make the bead change colors? Um, Extension, you can have the students actually create a radiation shield. You can do the engineering design process with that. They could use clothing, paper, boxes, plastic. I know some of the, there's performance sportswear out there now that comes with SPF ratings on it, which protects from the sun. I know a lot of fishermen, a lot of the fisherman gear comes with that SPF because you're out on the water, you've got the sun reflecting back up off the water. But you can also make a UV bead. I like this. I've actually used this with little kids and they go swimming, and you put the sunscreen on the UV beads, and whenever the sunscreen wears off the UV beads, they're no longer clear. They actually change colors. And so when the beads start reacting to the UV light, we know it's time to reapply the sunscreen to the beads and also to their skin. So it's not a matter of, hey, you can stay in the pool for an hour. Okay, no, it's time to get out and get new sunscreen. Now, when those beads start changing color, whoever's wearing the beads know, hey, it's time to put more sunscreen on. So I think that's got a really practical example. Through the eyes of NASA, why NASA? And there's several different, NASA will be testing new instruments and leveraging the skills of citizen scientists to expand our relationship and understanding of the sun, earth, moon system. Beyond spacecraft, we've got experiments on the ground. I know there's planes, there's balloons. I know there's 11 NASA and NOAA satellites, 57 NASA-funded suborbital balloons, ground-based observations, and citizen scientists. So this is going to be an amazing day of gathering data to study the sun. This photo just kind of gives you a big picture of the different satellites that are out there. It's a little difficult to see here. And then some of the missions that are already out there. We know that the Solar Orbiter is coming. We know that the Parker Solar Probe is coming. But SDO, which is the one that I highlighted earlier, SOHO, Stereo. So these are all different types of missions that we have that are looking at the sun. We also have events that are going to look at it from the ground, and the Citizen Kate experiment is actually the Continental America Telescopic Eclipse, and where they are actually going to study the dynamics literally across the U.S. And so you can see the St. Louis Arch, you can see the mountains, and literally it's citizens that are volunteers. They've been trained, and they're going to collect images from the West Coast to the East Coast. You can observe the eclipse from the ground. If you're not familiar with the Globe Observer or Globe Activities, Globes is a citizen science project, and you can get more information about it at globe.gov. But students can use an app to observe the eclipse and actually record different cloud types, different air temperatures, surface temperatures, and then submit that information as a citizen scientist. There's other apps, the iNaturalist apps that you can observe as far as plant and animal behavior activity. And then there's a link for even more information about experiments that can be done during the solar eclipse. There's all sorts of satellites that are outside the Earth that are going to be observing the Earth as well, so that we can see what it looks like from space looking back towards Earth. They're going to be studying the moon while the eclipse is going on as well. So just all sorts of different ways that NASA is going to be taking a look at things. Again, additional outreach activities that you can create as far as making your own cardboard projector so that you can see the eclipse from inside a cardboard by using the sunlight. You can use a mirror from an envelope. Again, this is just safe ways that you can view it. You can do the pinhole cards or pinhole projectors. Again, the STL files are available. And then they're asking that once you do that, if you want to do an occasional selfie with your shadow next to the shadow of your state as projected using that STL file, that you can then upload it to the Flickr site there. So kind of neat ways again to be involved in this nationwide, possibly even worldwide event. Here's a list of all sorts of different citizen explorers, different ways, again, that they can be involved as citizen scientists. These are all links within the PowerPoint. You can also use the Google Science Journal using your phone, collect data. There's accelerometers, magnometers, light and sound sensors, just amazing different ways that your students can not just step outside and observe the eclipse, but literally be an active participant. There's additional NASA resources here, and again at the end of the NASA video, not the NASA video, but the NASA PDF document, those links are there as well. As a singular event of national science, of national scale with a global audience, there's a potential that this event will be something of the moon landing in 1969, and that's a quote by Dr. Lika. You know, for those that study the sun and heliophysics, this is a landmark event for a new generation, and I think that students will be talking about this for years to come. And one of the things that I hope that you and your students are able to say, you know, where were you on Monday, August 21st?